out there, that's not the case. This is just one study. It's a big study out of Stanford, 300,000 people, where the median temperature, oral temperature, was really 97.7, they had found. This one says 97.5. The more important point there is there's a spread. That bottom of the box is the 25th quartile, 94.6. The top of the box is the 75th quartile, 99.1. So what that means in today's world, if your normal healthy baseline is 94.6, you go to a physician's office, they measure you at 98.6, they'll tell you you're healthy, everything's fine, what are you doing here, go home. But I guarantee if you're up 4 degrees over your baseline, something's off. And so that's a big theme of our work. I'm sure it's a big theme of the HLI clinics here. Know what your healthy baseline is so you can detect those shifts. So your health, I think you'll appreciate, it's influenced by many things. It's influenced by your DNA, your genome, but also all these other things as well. And if you look at lifespan in general, 16% of lifespan actually comes from your genetics. There's a big error bar on that, but many of these other things we know impact your health span. That's exercise in the top right, food, stress, environmental exposures, all these impact. We know that intuitively, but we're in a world where we can now measure all of these things. Some pretty well, like exercise. I'm talking about wearables in a minute. Food logging, still a little bit clunky. Mental health is we can measure indirectly. We actually have some big projects doing environmental exposures that we're following as well. So even if you don't measure these directly, of course, you can measure their effects by actually the deep omics profiling, the sorts of things that we do and you do. And that's thanks to the revolution in these technologies, obviously genome sequencing. The cost for reagents is about $100 now with certain technologies. It's been quieter, but mass spec has had a pretty strong impact, obviously, on the biomedical revolution, where you can now profile thousands of molecules. And we would argue the wearable revolution that's spun out, mostly started out as fitness trackers, but these days these are pretty powerful health monitors, is really changing the way we actually collect data and think about people's health. And so many years ago, actually when I first moved to Stanford in 2009, the next year we set up something called personal omics profiling. The idea of collecting big data around people with the idea, many things were done with this. So let me say what we do first. We sequence their genome, and then from their peripheral blood monocyte cells, we'll look at the epigenome and a subset, transcriptome, proteome, cytokines. We had early on metabolites and lipids. The first ones, epigenome, proteome, and transcriptome, will measure out of these immune cells, and we'll measure the proteome, cytokines, metabolites, and lipids out of plasma. And then we'll also measure some of that out of urine. We'll measure the microbiome, we'll measure the gut. And for fun, for a research side, we also measure nasal, tongue, and skin. I had an interesting paper on that. I won't have time to get in that. That's on top of pretty deep clinical tests, questionnaires like stress, food. And then we have some advanced tests like stress echocardiograms. I'm not sure 100% what you guys measure here. And then we have a lot of different glucose control measurements because we're very interested in type 2 diabetes. I myself, I'm a strange type 2 diabetic. It's actually predicted from my genome. First time that had been done. And then we started on the wearables about 11 years ago now, back when they were fitness trackers and thought they might be powerful health monitors, so we added those on. And so one idea out of all this is to do very, very deep data collection, and the other aspect is to do it longitudinally. So we'll sample people every 3 months while they're healthy. And then if an adverse event like a viral infection comes along, we'll take 5 to 7 more samplings. And there are other times of interest as well. Like after interesting trips, we'll take additional samplings. And so you might say, why are we doing all this? Well, we're trying to understand what a healthy profile looks like, not a sick one. There are plenty of those out there. The goal at that time, this was back in 2010 when we started, was understand what a healthy profile looked like. How does it change over time? What's the difference between you and the person sitting next to you? What happens when you first get ill? And then important from the health monitoring standpoint, can we use advanced technologies to better manage people's health? And I can tell you when we started this at the time, physicians really didn't like us sequencing the genomes of healthy people. You may have run into that experience yourself. They said, this is terrible. I would literally get yelled at by them that, oh, you're gonna turn everybody into hypochondriacs, it's gonna cost millions of dollars. This is a really bad thing to do. Now, I think they've largely warmed up to this, but they're still not there for a whole body MRI, I guarantee. It's hard to find physicians that think whole body MRIs is a good thing. Anyway, we did get past that and did add that. And so with respect, I'll talk about a little bit about aging, but with respect to this idea about using advanced technologies to manage health, what we discovered, and again, this is a research project, but we had 49 major health discoveries just in the first 3.5 years on a small, I forgot to say, it's a rather small group of people, 109 people that we started with, still more now, some have dropped off, we've added more. It's a very eager beaver bunch. They do all kinds of fun sub-studies. But anyway, nearly half the people learn something really, really important. These are major health discoveries, some more minor ones too. And they span this wide range of areas, hematology, cardiovascular disease, metabolic, infectious, and so on. And so, for example, we caught someone with early lymphoma. 2 people with those pre-cancers, you can see MGUS smoldering myeloma. 2 people had serious heart issues. These are all found pre-symptomatically, I should say, and I'm sure that's what you're finding here. No symptoms yet. But these 2 serious heart issues, one's at RBM20, that individual, young guy, turns out had a heart defect. And once we got the sequence, around the same time, his father had a heart attack and actually passed away. And he got the stress that could follow up, and sure enough, he has a heart condition. And that was all figured out because we saw this genome change. And then the other thing, we picked up one through wearables that turned out to be pretty serious as well. And so the upshot of all this is that, you know, what we're doing is obviously getting a much more complete picture of people's health. And so again, I think I'm preaching to the choir a little bit here, but the idea is that, you know, we like to think we're getting, if your health is a 1,000-piece jigsaw puzzle, we're trying to get 600 or 700 pieces versus 5 or 6 they get today, which is really incomplete. We're just trying to get a much, much better picture. And again, I think that's a lot what you guys are trying to do as well. And then just from I'll just summarize this briefly, genome sequencing was important. 12 of the first 70 had a mutation that was highly actionable. That the red ones, for those who follow this, are the ACMG genes. The black ones, we went very deep in our interpretation at the time. Had these others, and 3 of these turned out to be actionable or were a big deal. They're all actionable, actually. The RBM20 is the heart defect I mentioned before. SDHB, you may know, it's if you have that, you're a high risk for certain kinds of cancers. One of those individuals, 2X means 2, one did a whole body MRI, and sure enough, they had early thyroid cancer, and that was removed, and they were able to keep most of their thyroid. Also a very young person. And then 9 individuals were thought to be type 2 diabetic. One turns out to be a MODY mutation, which is a different kind of diabetic, and they were on the suboptimal medication for years, actually. So this all turned out to be useful for, they're all screened more as a consequence. One person had a BRCA mutation. Forgot to say, these are single gene Mendelian cases, in case that wasn't obvious. Now, most diseases you may know, they're actually complex disease, like diabetes, coronary artery disease, what have you. And I won't have time to get into this in detail, but I can steer you to our papers. And complex disease is different. It's thought to be due to common changes, of which we have many, that are very small effect. And if you're unfortunate and inherit a lot of the bad alleles, you wind up a high risk. And if you get the good alleles, you're at low risk, so the good variants. And so people built these polygenic risk scores, which to be honest, don't work very well. They work for the top 2 to 4% of the people. And that, if you look at something called an odd score, you can see that. But they actually don't work well for most people. We think there are 2 flaws with that. One is the fact that, I won't get into this in much detail, but we think the reason is that polygenic risk scores are done by linear addition of variants, and genetics isn't linear for anyone who's done this sort of thing. And they also ignore all the rare variants. So I won't have time to get into this. Oh, I was going to like to say, yeah, so these single gene mutations like getting clobbered by a sledgehammer, whereas these small variants of low effect, or these common variants of low effect, are like death by 1,000 cuts. So anyway, that's the analogy I use there. So anyway, we won't have time to get into this, but we've come up with new ways of analyzing genomes by AI before it's popular. We can find anywhere from 10 to 100 times more genes with these new methods. And some of them methods take into account the rare variants. And what we're doing is looking for combinations of rare variants that put you at risk for these diseases. And abdominal aortic aneurysm, we even have a predictive score. I think I took that slide out in the interest of time. We'd found 60 genes where 3 questionable genes were known before. ALS, you may know, pretty debilitating. There were 7 known genes with our new method, different method. We actually came up with 700 genes, and we don't have yet a predictive score. We're working on that. We have a prognostic score, like how severe it'll be, but we don't yet have a predictive score. I know we can get one. We just need more work. And even severe COVID, we can find the genetic basis. So these new AI methods are very powerful, and I hope they're going to lead to better prediction than we could do now with these common disease. We're applying this to lots of conditions. These are now just 3 examples. And you can look some of this up later if you want to see the details. Now, the other thing we're doing as we're profiling people over time, we can detect changes, which we're interpreting as aging, at least when you look at the healthy profiles. And what we discovered is that even from the small cohort, everybody's aging differently. So we're following the biochemical pathways. And person 2, for example, their top biochemical pathway that's changing is their cardiac hypertrophic signaling pathway. They're a cardio age. Whereas the person on the left, their immune system, I didn't show up, but their metabolic and other aspects are changing as well. They're aging in several categories. And we call these ageotypes. And at the time, we were only powered to find 4 because the numbers were small, but now we can do more. But kidney, liver, metabolic, and immune were the ones. So each column's a different person. Each row is an ageotype. And so the 4 people all the way on the right, they're aging in all 4 categories: kidney, liver, metabolic, and immune. The first box on the right, they're not much of a kidney ager, but they're aging in the other 3. The second box here, I know I'm stepping out of your thing here, but the second box to the left, that's a kidney ager, but not aging, the other category. And then the one all the way on the left, that's kidney and metabolic. So again, everybody's aging differently. And the nice thing is, I won't get into this, but there are clinical markers associated with this. So it's actually actionable information. And for some of the metabolic agers, they've actually basically changed your lifestyle and improved their markers. I'm not saying they got younger, but they certainly improved their health markers. And we'll come back to this at the end. So we think this is pretty powerful. Now, more recently, we started looking at across the cohort and said, well, everybody assumes we're all aging gradually, right? You just get older gradually. And we decided, well, let's look at this in a nonlinear fashion. Let's look across windows and see how people are really shifting. And what we discover, first of all, most molecules will change. We can see the pathways that are changing. But if we ask where most of the bursts of change are, well, it turns out there's a big burst in the around 44. Don't take that so literally. It's a broader window than that. And the other is in the 60s. So these are 2 big times of change. Now, the one in the 60s, I think we expected, right? Because that's when disease risk goes up, when you get your immune system's on the decline, that's why you get vaccinated. And the one in the 40s sort of makes anecdotal sense. Many of us who've been through our 40s, know that's a time when you seem to injure yourself and such. But what's kind of nice about this is that as we look through these molecules, we can see the biochemical pathways that are changing, right? We're trying to get in molecular detail what's going on. And so this is really complicated. You have some sort of white thing that keeps blocking some of this, but it turns out that skin and muscle changes occur at both these times. Again, the one in the 60s we expected. All you have to do is look at someone in their 60s and you can see their skin's changing. But it's well known your muscle changes, people get sarcopenia. I'm not so sure it's as obvious for the 40s that's the case, although again, people do injure themselves. It's extracellular for the, I don't know how sophisticated the whole audience is here, but it's your extracellular matrix and some of your tissue connected proteins and key muscle proteins that are shifting. There's cardiovascular disease risk of both. We did pick up the immune shifts going on in the 60s. We see carbohydrate shifts. And we actually see kidney function shifts pretty severely as people hit their 60s. In the 40s, we'll see lipid metabolism shifts. And, again, it fits a little bit with the LDL that's out there, although it's not as obvious. But I think it also fits with the idea of people's fat distribution shifts. I'm not sure how much you notice that in the MRIs you're doing, but people's fat distribution does shift as they hit their 40s. And then other things that are interesting and probably worth being aware of, like alcohol caffeine shifts occur in your 40s. So we can see these changes, and there are other things that change by following this as well. So again, we think this is powerful because by knowing this, for example, knowing your lipids could go off in your 40s, both your physician and you might start paying close attention, maybe go on statins, don't wait as long. These are pretty safe. So it is actionable information. Now, how do we actually spin this out? Well, you guys are obviously doing, we are doing, in our case, we took a medical, we thought about this a lot before deciding exactly what to put out there, because what I showed you was a research project. And so then the question is, you know, how do you actually get this out to the broader community? Well, in Silicon Valley, of course, you form a company we form is QBio, and they're basically doing a medical version, an actionable version. They don't do RNA-seq because the physician won't know what to do with that. I'm not saying that's not valuable, but that's more research. That's the kind of thing we can take from the lab, discover, and then bring in. So they do more actionable medical information. I'm told some of you have done this. And as I'm sure you guys will appreciate, multivariate means that there are multiple lines of evidence that this is just from the first like 100 people they found early. I'm sure you found something similar. I've seen your first paper that came out, ovarian cancer, prostate. These various things were picked up through these deep profile, all pre-symptomatic. And the same is true for the longitudinal profiling. That often picked up, like we found early pancreatic cancer, which you wouldn't find if you didn't do these deep data. Again, I think preaching the choir a little bit here, but you get the idea that you can follow this. And I think this is going to be very, very powerful. In this group, so we've stayed on more medically actionable, and they have some other technologies they've been developing too. Now, the other area that we pushed very, very hard on, actually, when the fitness trackers first came out, was this idea about doing remote monitoring. We've been pushing two technologies. One is the wearables in general, and the other is this home microsampling, where you give little drops of blood, you mail it in, and then we measure now thousands of analytes and give you back the results. Starting with the wearables, you probably know there are, you know, over 1,000 devices out there, mostly watches or rings. I'm not sure how many of you are wearing a smartwatch or ring. Not everyone? Really? Oh, that's surprising. All right. Well, I highly encourage it. They're powerful, right? Because they measure 24/7. And the heart rate, resting heart rate variability, they're pretty accurate. They're not too far off. Certain things are off, like SpO2, depends on the device, depends on your skin color. But the deltas are fine, meaning you can see the shifts, and that's why they're powerful. And they measure things that they're measuring you all the time, which makes them super powerful. And they also, they can even measure things that we don't normally measure in doctor's office, right? Skin conductance, which actually has medical information. You'll see in a minute. And so early on, we put these on our cohort. We discovered actually within a year that you can tell when people are getting infectious disease. I won't get to all the details here. And this is actually a personal story. We discovered it because when I first got Lyme, I actually noticed that my heart rate went up and my blood oxygen dropped. I was on an airplane at the time flying to Norway. And I saw your blood oxygen drops on airplanes anyway. You may or may not know that. Most people don't. That's why you get tired on airplanes, actually. But anyway, my blood oxygen dropped abnormally low. You can see this is the last flight from Frankfurt to Oslo. That's that blue at the bottom there. When I landed, it never came back. So my heart rate was up, all pre-symptomatically. And I later learned my skin temperature was up as well, but I didn't notice that at the time. And then I did get symptoms off and on. I went to a physician after a few days, and I told him it might be Lyme because 2 weeks earlier, I'd been in rural Massachusetts where most ticks are Lyme infested. And so I thought the timing was a little suspicious. I went, it was Lyme. He draws blood, sees my monocytes are up, says, yep, you've got a bacterial infection. He wanted to give me penicillin. I said, no, I need doxycycline. Got a little tense there because physicians don't like that kind of thing. And he did give in, and he gave me doxycycline. And it cleared it up right away, which was nice. And then when I got back, I got tested right away. That's that plus, and I was Lyme positive. But I even had some antigens left. And it's a well-controlled experiment. You can tell I measure myself all the time. That negative, as before I left, I gave a sample, and sure enough, I was negative. So I seroconverted during that time and had antigens. And so the point out of all this is I could tell pre-symptomatically when I first got ill from a simple smartwatch and a pulse ox. And I forgot to say, you can probably tell I'm a big fan of all this stuff. So I'm down a watch because one broke, and I have an Oura ring. And normally, believe it or not, I wear hearing aids that are also sensors as well, which I think are going to be very powerful, especially for older folks. And now I lost them. That's one minus with hearing aids. Lost them on an airplane, but I need to get them back. I wear them for hearing, by the way, but they're also sensors as well. I can still hear, just not as well. All right, anyway, so when we first discovered you could tell Lyme disease, that was nice. And then we had 2 years of data by the time we analyzed it all. And we looked for whether we could tell whether you got respiratory viral infection. And sure enough, it turns out I had my resting heart rate had jumped up 3 times over that 2 years. And one was a Lyme time, 2 were viral infections, and the third was a time when I had high C-reactive protein, but I had no symptom. C-reactive protein, you may know it's a measure of being ill. So every single time I could see this from a smartwatch, and I could see it in advance of symptoms because I always track this stuff. And so we wrote algorithms to detect that, and it worked on me. It worked on 3 other people who got sick twice. That you could tell when people are getting ill because your resting heart rate jumped up in advance of symptoms. And we published that in 2017, and that was nice, and we were very excited. And then, of course, in 2020, along comes COVID, and we said, oh, we better see if we can use this for detecting COVID. If you think about how we detect COVID now, we use temperature, which is a 300-year-old concept, and it doesn't work well for COVID, right? Half the people don't get symptoms. When I got, or at least a fever, fever, well, a lot of people don't get symptoms either. In my case, I didn't get a fever when I got COVID. And so we don't think that's the best. We think, antigens and PCR are nice, but you don't do it all the time. It's inconvenient, whatever. And therefore, smartwatches, we think, should be powerful for detecting this. So right away, when the pandemic hit, we partnered with Fitbit, got 5,300 people enrolled. 32 of them had COVID while wearing their smartwatch. And they had a diagnosis day and a symptom day. And this is our very first case. The top graph there is resting heart rate. It's a standard deviation plot. And day 48 in purple is when this person was diagnosed with COVID. Day 47 is when their symptoms first appeared. But you'll notice their resting heart rate jumped up 9.5 days prior to symptom onset. It's a very clear signal. It's easy to spot. And in the end, we discovered that we could tell for 80% of people, 26 of 32, we could tell when they were ill in advance of symptoms just from resting heart rate because it jumped up. And then we wrote an algorithm that follows people in a circadian fashion, looks for a jump up in signal, and if it's too high for too long, it gives red alerts. And so we've now set that up, and I'd love to have all of you, in fact, maybe we can share this link later. All of you are welcome to join our research study because I want to perfect these algorithms better. And you'll see why in a minute. So anyway, this is our real-time detection, one of our first cases here. This person's symptoms showed up on day 21. Day 22, they're diagnosed, but they're getting red alerts for 3 days prior to symptom onset. Very, very sensitive measure. Works 80% of the time. That's why we need you to sign up. This is just with resting heart rate mostly. At the time, it was hard to pull in heart rate variability and things. That's what we're pulling in now. So I know we can get these signals better. And it's very, very sensitive. It works for Apple, works for Fitbit. It should work for all devices, including Oura rings. And it also even works in asymptomatic cases. So this is an individual who was diagnosed with COVID at the arrow there. But they're getting red alerts for 2 weeks prior to symptom onset. Again, because their resting heart rate jumped up. And I can tell you it's even more sensitive antigen tests. This is me, but we have other cases as well. In my story, I was actually getting ready to go to New York City, and I woke up that day, and I'm a little congested. And you know how when you're just a little congested, when I come down with something, is it allergies? I'm not sure what's going on. So I got an antigen test because it was that day trail 2022. I was negative. That's where the T is. My antigen test said negative. I looked at my smartwatch and it's positive. That's the day 10 here. And so what I did, well, I got on the airplane and went to New York City to this meeting. But before you could go to the meeting back then, you had to get tested. And sure enough, I was right positive. So I spent a whole week in a tiny little hotel room in New York City all because I listen to my antigen test and not my smartwatch, okay? Smartwatch is more sensitive. We have other examples as well. We think you need as little as 2 beats per minute and you'll pick it up. Again, because it's measuring you all the time, so it gives a strong signal. Now, I want to emphasize it's not specific for COVID. We've lost it again. I need your help. No, next slide. There we go. It's not specific for COVID. Other things will trigger red alert. And some of this is obvious, like if you run a marathon, your heart rate will be up for a few days. That triggers red alerts. Other things listed there, other infections will trigger red alerts. That's why we want more data. But the number one trigger of red alerts, these are in COVID negative cases, is workplace stress. So it's a mental health sensor as well. So the bottom line out of all this is that if you're sitting around not doing anything special, you get a red alert, you're probably either mentally or physically stressed, one or the other. And we would recommend you get it checked one way or another. So again, some of this is easy to contextualize, some you should check. All right. We think this is the tip of the iceberg because if you think of what smartwatches do, they're shining light onto your blood and they measure, like when they're measuring blood oxygen, they're measuring spectroscopic shifts. Okay, that's what happens when your blood oxygen binds heme, it shifts. And it measures all kinds of stuff then in this, I mentioned galvanic stress response. So with the 2016 device, which is not particularly high resolution by today's standard, we did machine learning on features from the smartwatch and look for if we could predict clinical measures. And sure enough, not too bad for red blood cell count, hemoglobin, the 3 left ones. We actually can get a pretty good signal. Even hemoglobin A1C and fasting glucose, we can get a signal. They're not clinical grade measurements, but they're good enough to detect shifts from your baseline to see when something's going off. And again, we think that's the power of all this. The other thing we're doing a lot with our continuous glucose monitors, how many of you have worn a CGM? Ah, fair number, good. So these are powerful, you may know, because they measure your glucose every 5 minutes. And at the time we got involved with these, they were being worn by insulin-dependent type 1 and type 2 diabetics. And our claim to fame, if you will, is we just started putting these on normal and pre-diabetics. And what we discovered is that some people have good glucose control, like the top line there, pretty stable. The one in the middle is a moderate spiker after eating. And the one at the bottom is a bad spiker, just as bad as diabetics. It's thought to be was thought to be normal. We think it's how it's measured. And so we wrote algorithms to classify people into glucotypes, low, medium, or high, based on their glucose levels and spiking. And so that was quite nice. And then the other thing we discovered quite early is that different people spike to different foods. So some people spike to potatoes, others to pasta, some to white breads, and the brown bread. We're all different. And your microbiome accounts for about 21% of that. Now, this was also found by Aaron Siegel, and he published a paper just before us. And in fact, found that, here, same thing. So here, this top participant here is spiking to banana, but not a cookie. Probably the only person on the planet doesn't spike to a cookie much. This person spikes a cookie, but not a banana. That's very common, all right? We had found actually that some people spike to bread and peanut butter, others to protein bars, which often have carbs, don't let them fool you. And 80% of people spike to cornflakes and milk. That stuff's nasty. I highly recommend against it. It's not, if you don't remember anything in my talk, that's the one thing you should probably remember. Now, more recently, we haven't published this, but we had 55 people test the identical amounts of 7 different carbs, on successive days after fasting to see what their profiles look like. And sure enough, everybody spikes a different foods. Just like you said, this person here, you can tell by the color, their top spiking food is bread, next one's grape, next one's pasta. Next one, I believe, is potatoes, that yellow line. Most people actually in this one, they'll spike to white rice. Okay, so we're very curious, what's going on here? Why does this happen? And there are many ways. I mentioned the microbiome is part of this, but we also want to see whether your diabetic subphenotypes might do this. Now, diabetes is a very, very heterogeneous disease. Involves multiple organs, liver, pancreas, muscle, brain even, there's like glucose metabolites, and all kinds of pathways which have gotten a lot of attention, incretin, for example, and all kinds of molecules. So it's a very complex process involving many things, and we don't think diabetes is a single disease. We think it's many, many different ones. So we've gone in and subtyped these 55 people, starting with the first 36 here, and we wanted to see what's going on with them. And so we started, and the ultimate goals are related then to food spiking. And so this is people's hemoglobin A1C. Blue is actually their, these are normal folks, yellow are pre-diabetic, so we had one diabetic. And after subtyping with some pretty sophisticated text, I won't get into this, you can see they have different varying degrees of muscle insulin resistance, beta cell function, incretin, which is this hormone made by your gut. The GLPs, Ozempic's an analog of that. And there's hepatic insulin resistance. And so you'll see different people have subphenotypes. A better way to see it's on that map. So each row is a different person. If you look at S42 all the way on the right, that bright red one, that's a person has an incretin defect is the first problem. And then looking over on the left column, S40, roughly 31, 44, 41, these ones right here, I will step over there. Their main problem is muscle insulin resistance. So different people have different subphenotypes. I didn't say, but I'm a type 2 diabetic. I actually have a beta cell defect. I'm insulin sensitive, and I make insulin just fine. We figured out through all this profiling. So we're all different. And then the question is, well, how does this relate to phenotypes? Well, it turns out that if you're insulin resistant, you're generally a potato spiker, okay? And why that's the case, we can speculate and talk about that. Whereas insulin sensitive folks don't have that problem. Both will still spike the rice. And also you tend to spike the pasta as well. So this is what we're trying to do, correlate your subphenotype with the individual, your food response. And these days we can actually figure out what your subphenotype is just from the shape of the glucose curve on a CGM. Won't show you that, but that's going to be very, very powerful then for trying to understand what's wrong with you, your type of diabetes, and then correlate, or pre-diabetes, which is where we're trying to operate to keep people healthy. And then relate it to food. That's where we're going with all this. And so here's the other direction we're going. We've actually profiled these people very deeply. I forgot to say, but we did validate what I just showed you on a separate cohort. So we took a set of people wearing CGMs, and we very carefully monitored sleep, activity with these watches, and diet for quite a bit of time. And then we relate it to subphenotypes because we want to see how to match lifestyle and actually timing of lifestyle, you'll see in a minute, with your subphenotypes. What should, if you're insulin resistant, what should your behavior be? That's the kind of thing we're getting at. And so it turns out that you can actually start correlating, building predictive models, have a bit of a conversion problem here. Again, we're measuring both activities and timing of activities, not just activities with, and here's a simple measure related to hemoglobin A1C. Well, sleep, if you sleep longer, you'll have lower hemoglobin A1C. Most people don't get enough sleep. And that's actually known already, okay? So we get negative correlation. I think that top one is starchy carbs. Sorry, I got all messed up here, but that's expected too, right? Bad carbs, you're gonna have higher hemoglobin A1C. You can make all these different correlations here, but we can do this for subphenotypes as well. See muscle insulin resistance. Well, it turns out if you exercise more and longer, I should say, you'll improve your muscle insulin resistance. So these are the kinds of associations we can make. Same with true for some of the other subtypes as well. And then we try and put it all together where we put in people's lifestyle and try and make recommendations around this stuff. So what should you do and when should you do it? And as an example, this is complicated, so I won't have time to get into it. But imagine you're insulin resistant or sensitive. What's the best time to exercise? Well, the data can tell us that. Turns out if you're insulin resistant, the best time to exercise in the morning, you'll have lower glucose the next day. If you're insulin sensitive, you should exercise in the afternoon and you'll have lower glucose the next day. So it's not the same. So this is the kind of thing we're teasing out from the data we're generating. And so our company, we formed a company again, January. I forgot to say I'm conflicting everything I'm telling you, as you could tell that. And what they've done is they built a program, a whole app around various activities, and they have a 32 million food database. I'll put a little plug, you might want to partner with them. And they can basically track all these things. And people do their program for 28 days, where you can do the rest of it without a CGM. They improve their time in range. I see I left that out. And then they'll also lose weight. And that wasn't even the main goal, losing weight, but improving time in range there was a main goal. And that's true for normal, pre-diabetics, and diabetics. They all improve. So these are very powerful. Again, if you wear a CGM, you'll never eat the same because you'll see what spikes you. And these guys have a food database and other things they recommend that go with that. And now they have a version without a CGM, believe it or not, that can predict your glucose spikes. It's not as good as a CGM, but it's not too bad. And so it's a simple way to actually better control your glucose. So something you might do, make introductions of that interest you. All right. So then the other thing I might say is we're very interested in this idea of doing home monitoring, or at least home sample collection. And so we build an app to pull the wearable data, microsample data, see, the users can see what's going on with their profiles. This is Mike Snyder's world. I envision a world where people get sequenced before they're born, and then together with biochemical wearable data collection, can better track their health, try to keep people healthy. And then, as I say, been talking too long. All right, I hope I don't have to start over for those of you who are online. So anyway, we do spin off companies, and some of which would probably make sense to partner with you if you're interested. QBio is probably fairly overlapping, but January AI is a CGM. They spend a lot of time, a lot of science behind what they're doing, build these CGM monitoring systems and the database. We have a smartwatch company. We have a company that's pretty good at long COVID. And then this one up here, I'll just mention Iolo. I know you do metabolic profile. They do a targeted assay at quantitative profile. They do the microsampling. You mail in your microsample and they measure 600 metabolites. And at the end, need your help one more time. I'm wrapping up here. I need your boost here. No, I think, can we go back? Yeah, I think we jumped over two somehow. Yeah, can we go back two more? They got, well, oh, keep going. Yep, one more. Right there, stop. All right, so they'll measure these 600 metabolites, cover 20 wellness categories: oxidative stress, inflammation, all kinds of useful things. And that one over there is longevity. So next slide. So we can tell people's biological age relative to their chronological age. But what's nice is from metabolic profile, we know roughly where the different aspects lie. So if you get a methylation test, they're great. They actually work pretty well, but they're not actionable. What's nice about this is that you're measuring these different categories and can see what to act on based on the data they have. But you can see the various markers for heart age, for metabolic age, and inflammation. So this person's older than their chronological age. And their inflammation, not a good thing to be, by the way. But the nice thing is their inflammation's fine, their metabolic's not too bad, but their heart age is a lot older. And then of course you use AI to pull in the data to actually then makes very specific recommendations, not just exercise more, eat better, but specifically what you should do. And again, there might be room for a partnership here because they're very well set up for this sort of thing. So it might be something you consider. So I think what they're doing is pretty cool. I'll jump over though. This summarizes everything I've been telling you, and we're running a little late. I know we started a little. And I have an amazing team who's actually been involved in doing a lot of this. Again, this is a research project, everything I've shown you. But the way we translate, it's not unlike what you're doing, try to scale it so that we can get it out to the world and try and benefit everybody. That's the plan. So thanks again for having me here. If it's not too late, I'm happy to take a few questions or whatever you like. Gonna run out again?
Thank you so much, Dr. Snyder. We're gonna take some questions from the crowd, and also anyone who's attending virtually, please feel free to submit any questions in our Q&A section. So yeah, please.
You need to shout, or should we repeat it?
I'll repeat it. Yeah.
So a couple questions for the
Yeah.
What in terms of the variations or say pre-COVID, how many?
So I think the question is in terms of COVID resting heart rate, what is the variance there? Is that correct?
We'll pick up. So I would call it a stressor alerting system, and 2 beats per minute is the way we have it set. Now you can dial it up or dial it down. But we set it so the alarms go off about every 6 weeks. We surveyed people. They found that to be, fine, meaning it's not pinging them every day, something's wrong, but often enough, and we have reasonable sensitivity. And that gives about 2 beats per minute will generally work. Now, some people have more variation. Remember I said 20% of people we didn't get? Well, they tend to have a lot of fluctuation in their resting heart rate. So they're harder to pin down. So it's going to come down to the person, but if you have a fairly stable resting heart rate, we've written some algorithms to try and avoid the noisy times. yeah, you can pick it up pretty well. And that 2 beats is not very much, but most people are higher. The average, I believe, is about 8 beats per minute. People get COVID when we first got our red alerts.
To be honest with you, what is happening? You are
That's a great question. I think what's happening is it's engaging your immune system. IL-6 kicks in, which is known to raise temperature, although we don't always see that. So I'm guessing this is fluff because yeah, basically it's your immune response, I think, is kicking in, and that's probably taking a lot of energy, my guess, because I think it's happening faster than, say, your increased respiration. Your respiration defects show up. Again, it shows up pre-symptomatically. So I don't think it's a respiration. I think it's more of an immune trigger that's somehow coupled to resting heart rate. And that's actually been shown that you can tweak people's nose and actually increase their heart rate.
when I exercise, and when I exercise cardio one day.
Yeah. Well, my guess is you're a pretty intense exerciser if it's staying up that long. If you're in good shape, you recover fast usually. And so you can come back to your baseline pretty quickly. Now, it is the case that, like when you run a marathon, your heart rate will be up for several days. So it does get tricky. So the best way to set up these patterns is to build it around your own circadian pattern and try and keep regular patterns, which most people do. Like I exercise every morning. So of course my heart rate is up high then. It's not my resting heart rate though. But I'll tell you, my glucose goes off because I lift weights, and that breaks down glycogen and spikes your glucose and has others. So it helps to be aware of these things so that you can interpret your data. But we build our algorithms, and we have further to go, like weekdays versus weekends. And we don't have it fully integrated yet, but the plan is for women to build in monthly cycles and that sort of thing. So because you'll see fluctuations in physiology across, the menstrual cycle. So all that should be built in to get optimal, detection algorithm. We're not there yet, but we're partially there, and we've accounted for some of it. Yeah.
You mentioned how the polygenic risk isn't the
Oh.
best tool to assess risk, especially because it just focuses on the European population. Is the genomics community worldwide coming together to build a better tool? There's a lot of data out there, and with that population.
Yeah. Well, there's a big effort to obviously include more people, like the All of Us program. My own view, is this going live or is this staying internal?
We could treat
Okay. I think that polygenic risk scores is dominated by the statistical geneticists who are totally into linear genetics. So they're never going to get much better than where they're at now because genetics isn't linear. And I can see it when I send their papers with these new, what do you mean you got 100 times more genes? That can't be right. You have something wrong. And we're 100% right. We validate it. We even go in and CRISPR knockout, the dominant genes, and it's right. And so it's going to take time. They're as bad as physicians, these polygenic risk score people. So they just don't get it, that genetics doesn't work that way. So that's why I don't want that live. Or if you make it live, cut off the Q&A. Yeah, go ahead. Thank you.
announcement is actually Stanford biology 50 years ago.
Okay.
And I'm also a master of IO. And
Okay.
because you have a portfolio of mentioned, I'm very happy.
Try them all.
Yeah,
Try them
I know.
all. Yes. Okay. Sorry. Go ahead.
I never saw that I have.
Yeah.
So I started to cut down some beef.
Okay.
Yeah. So my question is about so recently, one of the friends with the Marvel CTO Zaha, who passed away. Then also Princess Kate survived after cancer.
Right.
So for this type of news, what's your first impression like? Even though they both got early diagnosis, but the outcome often varies. Like, what kind of advice you would give people who
Yeah, well, welcome to heterogeneity of, this is the problem, right? Obviously, earlier is always better than later if you're going to stand a chance. So, but I mean, most, especially cancer, it's very heterogeneous in terms of its aggressiveness. People ask me all the time, how often should you get measured? And we honestly don't know the answer to that. I always say, well, it probably depends on what you're at risk for, what your trajectories look like. So if you're, at high risk for cancer, you probably want to get measured a lot more. If you think about when an aggressive cancer first comes, it moves fast. In 3 months. You can go from probably very little to something pretty severe, if not death. That's the extreme case. But I don't think, but there are plenty of others that are much slower growing and but that's very personal specific. I'm sure a lot of that has to do with how good your immune system is, quite frankly, because your immune system is your number one defense against cancer, right? It's clearing. We all have cancer all the time, and it's clearing it. So anyway, it's just the nature in cancer, as you know, it's a genetic disease. So different versions have different forms. Lung cancer is a classic where you have 5 different pathways mutated, and the drug you use will depend on those pathways. So unfortunately, and that's the problem. Right now, we tend to do medicine, one size treats all, but these diseases are subtypes, like the diabetes, good example. Having said that, the GLP-1, the agonists, the Ozempic agonists, do seem to handle a lot of different forms of diabetes. So maybe that one drug still doesn't fit everybody, by the way. And some people have severe reactions. Anyway, sorry. Yeah.
What is the rate of error? Like, is it really detect all? Do I know? Does it give false positives? Are there like certain more
You're asking all the right questions. So the question was, for those online, yeah, what's the error rate, for detecting and missing things and all that sort of things? And the answer is we don't know. These are good questions. We don't know what we're missing until it pops up later, right? If we didn't catch it pre-symptomatically, and there are some people who have had heart conditions that later popped up that we didn't catch early. Now, part of it's the nature way we're doing it. It's a research project, so we're not able to measure things in real time for all things. So, but that will be the goal, to do stuff in real time with quantitative assays and get better at. But the answer is we don't know yet. And this whole project, everything we're doing in lab is a learning experience. We do some markers. I mentioned the lymphoma case. We saw some interesting markers that went up about 9 months before that we saw the lymphoma, so that they are candidate markers for lymphoma. This is the kind of stuff we hope to pull out of a study like this. And I imagine you're doing the same out of your data as well. So some of this, it's still research. We're trying to see what we can see. And then once we validate it and get it going, then it turns into a real test, I guess. So you're asking all the right questions that we don't know the answer. Yeah.
So it was very impressive to see the papers that you published that this board in the 60s acceleration of reading, because you showed us things exactly on our that's from conditions, all these things. That means DNA methylation, RNA, or proteomics, have a lot of that we're having similar acceleration of throughout the entire country. But the thing that we're still knowing is what is the actual life based on the heart rate or accelerated. And according to the study, then we're having it all tracked. What is the actual lives? That's all.
Yeah. So I'll try and capture that. So you had seen this before. I didn't get your name, but with the methylation pattern. So I'm sorry if we didn't cite you on that. And then she says, what's the actionable information? And that's the problem with the methylation clocks. I think they're quite accurate for humans and probably other organisms as well. But, they're not, they can tell you when you're going to die and all that stuff, but they don't tell you what to do. I think that's the power of the Yeah, the metabolic aging clocks and the age types that we define, because we're measuring all the stuff and we can see in more detail exactly what's going on. And the nice thing about the age types is you can measure this as personal level. Meaning we think you need, for us, we'd like to do 4 or 5 measurements within 2 years, and we can see what that trajectory looks like. And as I say, the information is highly actionable. And I think IOLO has taken this to another level. And they've also made it easy because you can do the microsampling, mail it in, and get these profiles back in these different categories. So, yeah, it tends to be more, you know, they will say exercise and certain things. I want to actually prove that. On the food, they can tell you because if you more information you enter, the better, more specific recommendations come out. So if you tell them what you're eating and they see these things up and you put in your meds, they have to watch the med part because that information will go to physician, but not necessarily the person. You can't tell someone, well, this med might be causing that, and then they stop it and they could do something bad. But there are interactions between meds and a lot of those markers I said. So they'll tell that to the physician that, you know, there's an interaction that says this goes up. But the other sorts of things are, you know, I'll give you a simple one. This is one you know already probably, but oxidative stress, if that's off, well, eat more blueberries or other antioxidants, polyphenols, things like that. But if you're eating some of those already, obviously they won't tell you to do that. They'll steer you in other directions. So a lot of it's supplements, a lot of it's just, you know, obvious healthy foods, but there are things most people don't necessarily know. This crowd might know because you're probably pretty health conscious, but most people don't. So, yeah, great questions.
Yeah, so we're gonna take a few questions from our
Yeah,
webinar
then we'll take one
attendees.
more.
One of them is how do they become a participant in your studies?
We have a link on our website. Go to our studies. We have a ton of studies. To do the deep profiling, we might be re-enrolling again. You had to do fiber before. We're doing some cool fiber studies. But you have to be in the Bay Area because we're very anal about sample collection. We want everything to be just right for these research studies because can be a big source of heterogeneity we're trying to avoid. So for the deep profile, but some of the other ones like the CGM studies, the wearable study, anybody on the planet can join for detecting COVID. So sign up for us, and they're not all mutually exclusive. So some of them are, but please do sign up. We have a fun study of what's better, sprinting or long distance running. So we have 2 groups of people trying each, and we're profiling, you know, before and after and all that sort of thing. So that's a fun, you have to be in the Bay Area for that one. Same thing because of the way we're collecting samples, and we're looking for more participants. You have to start out sedentary though. So if you're a couch potato, join our study, and then you'll get randomly assigned to either high intensity, a long distance, or control. If you're control, a lot of people, nobody wants to be a control, so we discovered they drop out. So what we do is we say, well, be a control, and then we'll pop you into our one of the other 2 arms, but you know, not a total control.
What's the website?
Look up Snyder Lab. I think if you just look that up, you'll get fairly quickly to our suite of research studies. There's about 8 of them that are live right now. And some of them are around long COVID and this sort of thing too. It depends on the study. The wearable one is really easy. So. Some results you can get back right away, like the deep profiling one, you'll get back the clinical measurements. A lot of, because of the research study, we save up samples and then process them all in one batch. So that takes several years. So if you're lucky and just join right by the time we do the batch, you'll get your results back kind of quickly. But if not, yeah. So, but other kinds of studies, the CGM study, you can get back pretty quickly. That one's on hold because I think we've probably filled up for the moment, but we might reactivate that.
Okay. We have another question. Do you recommend doing a full body scan like Pronovo or another provider?
Or what's the other one?
Or another provider?
Well, QBio, of course. QBio first, HLI second, of course.
We had a question over there, right?
We did. There's now two over here. Yeah.
just
Go ahead.
for Dr. Snyder, I'm just curious, where do you see the field in the next 10 years?
I hope-
50 wearables you're wearing and.
No, I wear all these because I'm comparing things all the time and trying to push the technologies and that sort of thing. But in my world, I think the wearables can spread out very, very fast. I think the number one problem, and I'm sure you guys appreciate the same, is that our financial incentives are not aligned for keeping people healthy. That's why we practice sick care, not healthcare. We really need to incentivize the system to keep people healthy. And I think there's only two things that incentivize people. One is money and the other is family. So if we could give people a discount if they wear a smartwatch, or if you sign up for a health plan and you get, because these things are not that expensive and they'll be cheaper in the future, get a ring or a smartwatch as you join a health plan. And those people will live longer. I'm sure all of you who have worn a watch, when you get to 9,600 steps, you always walk those extra 400, right? You just always push yourself that little extra. It's not even a push. So I think you will incentivize better behavior if you keep this on. And you can tell when people are cheating and put these things on their dog and all that stuff. So we can get around that. And I think that would help. Yeah. But again, we have to get the financial incentives aligned to make that happen. Yeah. It's unfortunate. Yeah. Did you have a question in the back? Yeah.
People are complex. Not only I can know personality. Also have other things going on, like I had a fight with or somebody got bullied like that. There were other things. And how do you explain it?
Yeah. Right now, the answer is no, because it's been hard to get the data. These watch companies weren't sharing it very well. So the answer is we would have a hard time, but you would contextualize that. Like if you knew family stress event was happening, you'd say, well, that's probably due to my family stress. I know in the future with the right data types, we'll tell the difference between, say, a stress event of the sort you described versus, say, a respiratory viral infection, because your respiration rate, they're not going to be the same between those. So that's why I need you guys to join our study so we can build algorithms to make those distinctions. I actually think detecting mental health stress is important. So you might call it a false positive. I'd call it a true positive, but just for a different assay that we think is just as important. So we would like to capture that and distinguish these, which at some level we should be fine at. And I think this came up in one of the other, might have been your question. I think the way we look at this, we're doing the monitoring, but it doesn't prove any of these red flags that pop up. They're never ironclad, right? The next step is to go get it further checked out. But the fact that you're measuring things a lot means you can see what's going on better and go get it. If your heart rate's running up for a while, something's off. And you really should get that checked. And people have seen that in their own personal experience. And we're trying to make them aware. And some people happen to have listened to my talks and actually done that when they see things are off. And physicians will often miss it because physicians just don't have enough time to spend with you, right? 15 minutes is the average. So nobody can diagnose you better than you can diagnose you.
We have another question. And the question is, have you found any commercial supplements useful to improving health or longevity?
Yeah, I mean, I have my list of 10 supplements, or maybe it's 12 now. And I probably should put it up on a website, just haven't gone around to it. So what do I take? Well, I take in the morning, B complex, vitamin B12. You need the K2 to go with your D3. What else? That's for the morning stuff. I take, and I'll explain a few, Berkeley Lights, which is it's a nitric oxide producer, beetroot extract that actually promotes endothelial health and microvascular system health. And I think that's a big deal. I think that's underappreciated. So I take 2 of those tablets every morning. They're probably the most expensive thing. Well, I take coenzyme Q. That's kind of pricey. That you take, by the way, it's not just what you take, it's when you take it. So that you should take at noon, but I take it at night because I just remember at noon. And then at night, what do? I take, this might be, I don't know, this may not be real, but I take milk thistle, which is supposed to be a detoxifier. I take magnesium because as you get older, there is a need for magnesium. It helps you sleep. I don't sleep enough, and probably I should take more magnesium, I'm guessing. What else do I take? There's about 5 or 6 things at night I'm taking. Yeah, I'm forgetting some. Oh, vitamin E. So some of these are obviously antioxidant vitamin E. Yeah, the coenzyme Q, free radical scavengers. So yeah. So I think at the end of the day, you really want to have anti-inflammatories. You want to have antioxidants, and I'm a big believer in the microvascular system, as you can tell. So I think those I take baby aspirin, and yeah, because everyone on my father's side has died of heart problems, and then I take drugs for my diabetes. SGLT2 inhibitors are good. They actually promote heart health. And believe it or not, I'm on Trulicity, which is an Ozempic analog. So that's for my diabetes. And it really worked. It goes from hemoglobin A1C went from 8.3 to 8.4 to 6.3, just like that. Unbelievable. I'm a metformin non-responder, so that turned out to be good. All right, did you have one last question? Maybe.
Oh,
Okay.
I had 2 questions, somewhat related, but it's slightly different. I'm actually investigating a full body panic bio. I noticed that there's an MRI machine. Which one, and you remind me that actually is being available.
No comment.
And my next question was, you know, all these companies with all these interesting things, what's next?
Well, companies always start out in stealth mode, at least for me, because there's usually new technology built around them. This may or may not be. We are launching a grant writing company of all things. That's very different from all my other companies. And then we have some that'll launch next year. Yeah, I don't know if I'm quite ready to disclose those yet. But stay tuned. I may. We'll see. Yeah. So.
And one last question. Someone was asking what wearables do you specifically wear?
Which ones do I wear?
Yeah.
Oh, recommend. Well, part of that is a personal thing as well. So Apple Watch is higher resolution. You may know, especially when you say run, it captures your high heart rate better, but it's harder to keep charge. And the number one problem especially from the research side, is missing data. It's nice to have complete data sets. So Garmin and Fitbit are pretty good because they charge fast. 15 minutes, they'll charge for 5 days. But of course, the number one I recommend is my company, Multi-Omics. So, of course, but for most people, they're not actually direct to consumer. But I think for most people, the Fitbit and the Garmin's a better match, even though they're lower resolution. Just because they do keep them charged. The other problem with Apple Watch, a lot of people charge them overnight. That's the best time to be doing health monitoring. So, yeah. And the other thing I will say, though, don't underestimate hearing aids. They're going to be the future. They ask about the future. And it's just passive, great data collection. It's really amazing. Yeah.
Have you tried the 4th Frontier heart monitors with the heart rate?
The 4th Frontier, that's a company or a device? I don't know this.
It's a device.
Oh.
Changing that when you're exercising.
Oh, no, it sounds like I should learn more about. See, oh, please send me the link on that, or I'll try and take a note afterwards. Yeah, always looking for new devices. Yeah, so. Well, the one area that's the worst, and I don't know if this does it, is sleep monitoring. Everybody advertises sleep is great, and these watches, they are all right for latency, the time you fall asleep. They're pretty good for duration and restlessness. But those sleep stages, that stuff's worth. I don't know if it's worthless, but it's not accurate. And so we really are in need of better sleep monitors, which I think would be, again, it's a very understudied area that's really important for people's health. So, yeah.
All right. Well, thank you so much, Dr. Snyder.
Thanks for having me.
Thank you so much.
Thank you so much.
Sure, yeah, this is, great.
Okay. Happy if it makes sense to partner with some of these.